The frozen ceramic reality. Lunar water ice is functionally a structural ceramic that requires more energy to phase shift than it currently provides as a chemical propellant. The Prime-1 mission data, finalized this month, confirms that this ice is not a subterranean reservoir, but a vacuum-sintered mineral matrix. When the intuitive machine's Athena lander touched down on its side at the lunar South Pole, it inadvertently created a high-fidelity experiment in volatile behavior. The impact and subsequent thermal leakage from the lander's belly-mounted hardware caused an immediate sublimation spike that our sensors weren't originally positioned to catch. This accidental data drop is more valuable than a successful drill core because it reveals the specific thermal energy required to liberate volatiles from the polar regolith. Understanding this energy-to-yield ratio is the only way to move beyond the optimistic marketing slides of lunar mining and into actual engineering. The mechanism that finally gave us these numbers was the Trident drill, breaking the sintered matrix. Traditional terrestrial drilling relies on fluid lubrication and gravity, both of which are absent in the lunar vacuum. The Trident drill uses a percussive rotary actuator designed to shatter the sintered regolith rather than cutting through it. Think of it like a hammer drill on a construction site, but operating at 4 Kelvin. During its 33-minute operational window on the lunar surface, Trident exercised its actuators against a tilted surface, proving that the torque and percussive frequency could maintain structural integrity even in an off-nominal orientation. The constraint isn't just breaking the rock, it is preventing the heat from the drill bit from flash sublimating the very ice you are trying to sample. If the bit temperature rises by even 10 degrees, the sample off-gases into the vacuum before the spectrometer can register it. This delicate thermal balance leads directly to the detection phase handled by MSolo, counting molecules in vacuum. The MSolo instrument is essentially a ruggedized mass spectrometer that counts molecules based on their mass-to-charge ratio. It doesn't look for liquid water. It waits for the drill cuttings to off-gas as they are brought to the surface. In the vacuum of the South Pole, water doesn't melt. It transitions directly from solid ice to vapor. MSolo measured a nitrogen partial pressure of 10 to the -8 torr, a baseline that proves how effectively we can distinguish between lander-borne contaminants and indigenous lunar volatiles. The data indicates that water molecules were present in every activation, but the concentration was far lower than the 5% weight threshold many ISRU models require for economic viability. This delta between theoretical ice maps and actual molecule counts is the reality check the industry needed. It forces a pivot in how we calculate the energy cost of lunar operations. The Real Volatile Map. Marketing narratives suggest billions of tons of water ice waiting for extraction, but the Prime-1 data suggests a much more patchy, transient distribution. The energy density required to extract 1 kilogram of water from a 2% concentration regolith is significantly higher than pre-mission estimates predicted. The torque sensors on Trident showed that the subsurface regolith at Mons Mouton is denser and more resistant than the simulators at Glenn Research Center led us to believe. This means future mining rovers will need larger battery arrays or localized nuclear power just to overcome the mechanical friction of the lunar crust. We aren't just mining for water. We are fighting the geotechnical properties of a surface that hasn't been weathered in 3 billion years. This friction is the primary driver for the next generation of mission architecture, the energy density verdict. The Prime-1 mission proves that lunar ISRU is not a resource scarcity problem, but an energy delivery problem. By connecting the mechanical torque data from the Trident drill with the volatile molecule counts from MSolo, we can finally define the specific massive power plant required to produce a single liter of lunar propellant. The takeaway is that localized nuclear fission is no longer optional for sustained presence. The patchy distribution detected at Mons Mouton confirms that landing sites must be chosen for their proximity to power-rich zones like peaks of eternal light, rather than just high hydrogen signal craters. For engineers and strategists, this shifts the focus from prospecting for ice to optimizing the thermal cycle of extraction. We now have the baseline contamination models and the hardware durability specs to design the next phase of the lunar economy. Watch for the Artemis 3 landing site revisions coming in November. They will likely move further from the crater floor based on these specific density maps. Subscribe for more